speaker. We have one but very important keynote speaker, Anders Moller. He will speak for himself. You can find the description of him on our website. He has so many, I mean, he's the top, one of the top researchers in the area of static analysis. I don't even want to try to present him to yourself because he's too big comparing to us. So Anders, I will unmute you right now. So we are all ears to your keynote talk.
Thank you for the invitation. For a number of years, I've worked on program analysis for JavaScript. In this talk, I'll give an overview of an ongoing research project that aims to improve code quality of JavaScript programs by the use of automated program analysis, testing, and transformation techniques. We try to address challenges in software development that arise from breaking changes when libraries are updated. This is joint work with my students and postdocs, Martin, Benjamin, and Gianluca. I'm sure you all know this thing called JavaScript. This is an extremely popular programming language, especially for writing web applications. Most JavaScript programmers these days write software using the NPM package management system. In fact, NPM is the world's largest registry of reusable software. It now contains more than 1.5 million packages, and around 1,000 new packages are added each day. Most of the packages are libraries that the programmers can use so that they don't have to write everything from scratch. Of course, some of these packages are used more than others, but some of them actually have more than 45 million downloads every week. If you look at the dependencies between these packages, you will find that on average, each package depends on more than 50 other packages when considering both direct and transitive dependencies. And because there is so much reuse, in a typical JavaScript application, 90% of the code comes from such libraries written by others. So this is clearly a huge success, and it is an important factor in the productivity of modern software development. But everything is not perfect. Practically all packages that are used a lot evolve rapidly. There are frequent new versions with new features and bug fixes. And that makes it difficult to keep everything up to date. Here is a typical scenario. Some package A depends on another package B, which is currently available in some version, let's say 1.1.0. But now the developer of package B makes some updates to improve the package somehow and releases a new version, 1.2.0. This may have consequences to package A. Some of the changes in B may require changes in A. This leads to some interesting research challenges. First of all, how can we automatically detect if such an update of a library contains such breaking changes? Secondly, once we know exactly what the breaking changes are, how can we automatically find the locations in the application code, in this case, package A, that may be affected by those breaking changes? And thirdly, once we know which locations in the application code may be affected, how do we actually patch those parts such that the application becomes compatible with the new version of the library? Our answer to these challenges is that all this is possible using new automated program analysis and testing techniques. If you are familiar with JavaScript and NPM, then you know that NPM uses the so-called semantic versioning scheme. The idea is to use versioning to signal whether an update contains breaking changes or not. Here are the basic rules. A version number consists of 3 parts: a major version, a minor version, and a patch version. Now, if you have made changes to your package, you should increment the major version if there are any incompatible API changes. You increment the minor version if you have added functionality in a backwards compatible manner, and you increment the patch version if you only made backwards compatible bug fixes. For example, if you use a package that is updated from version 1.1.0 to 1.2.0, then there should be no incompatible API changes. This is a minor version update only, so you can safely use the new version. But this relies on a very fragile assumption that the package developer knows for certain whether a change is an incompatible API change or not. The short answer is that the package developer doesn't know that. It's very easy to make mistakes here and misclassify a breaking change. One reason is that JavaScript is a very dynamic language with weak encapsulation mechanisms. Another reason is the package developer and the users of the package may not agree on what is the API and what incompatible means. The problem here is that it is generally hard to define exactly what is the API of a JavaScript library. JavaScript is a very dynamic language, so you cannot just determine the library interface from the syntactic structure of the library code. There's often no clear distinction between public and private parts of a library. There's usually no formal contract between the library and the client. We generally don't even have type signatures for the library functions. This situation is very different from statically typed languages like Java. If you upgrade to a new version of a library in Java, then simply by recompiling your code, the type checker will tell you if, for example, a method no longer exists or now has 3 parameters instead of 2. Of course, the type checker doesn't detect semantic mismatches, only those that are type related, but that's much better than nothing. We want JavaScript developers to get at least this level of tool support for detecting breaking changes. So the first challenge I want to talk about is how can we automatically detect type-related breaking changes in JavaScript library updates? Here is a real-world example. Lodash is the most depended upon of all NPM packages. In total, 114 versions of Lodash have been released. I don't want to explain exactly how it was changed here, but this turned out to be a breaking change, a very subtle one that only affects clients of this particular function is iterative call. When this was discovered, the developers quickly released a patch update of the library. Here's the corresponding explanation in the changelog. The point is, if your code depends on Lodash and you happen to download and use the version with the breaking change, then your code would fail and your customers would complain. There is a quite simple way to detect many breaking changes by relying on the fact that many packages have test suites. If the test suite of package A succeeds before the update of B, but fails after the update, then there is likely a breaking change. So in that case, it shouldn't be a minor update like here, but a major update. So if we can find many packages like A that have a test suite and depend on the library B, then we may be able to test this update of B quite thoroughly. We've tried that on a large number of updates and packages, and we found that there are lots of breaking changes even in minor and patch updates. And most of them are type related. Basically, if we had static type checking like in Java, then most of the breaking changes would be detected by the type checker. But we also found that when one of these tests fail, it is generally very difficult to find out which part of the library is to blame. And it takes a long time to download and run large collections of test suites. So overall, if we want to detect breaking changes in libraries, it's not a very good solution just to run the test suites of the clients. Here is what we do instead. We call this technique type regression testing. We still run the test suite of the client, but now we don't care about the outcome of the tests. Instead, we monitor all the interactions that take place between A and B. And from that information, we build a model of the part of B's interface that A uses. We essentially learn the type signatures of all the functions that A is using. And by doing that for many clients, we learn the entire API of the library. Now, when the new version of the library is ready to be released, we repeat that process, this time for the new version. And then we can compare the two models and detect incompatibilities. For example, in the old version, maybe calling some method foo returned a number, but now it returns a string. That would be a type-related breaking change. In a sense, we have amplified the existing test suites. Even though this test suite was developed to test package A, we now use it to detect breaking changes in package B. If we try this for the Lodash example I mentioned before, we automatically find the breaking change. Strong params is one of the many packages that depend on Lodash. It contains a test that calls a method in Lodash, which ends up calling the isIteraT call function I mentioned earlier. Interestingly, the entire test suite of strong params still passes after upgrading to the new version of the Lodash library, but the models we generate are different, and thereby our approach succeeds in detecting the breaking change in the isIteraT call function. So what are these models? A model is essentially a map from a dynamic access path to a type. It describes how the client uses values that originate from the library, and conversely, how the library uses values from the client. For example, the model we produce for the Lodash library contains this entry. This part is the dynamic access path. It basically tells us how a value can be accessed from the client code. And this is the type that has been recorded. What this tells us is that in some execution, the toString property of the third argument passed to the merge method of the object obtained by loading Lodash is a function. If that changes in a new version of the library, then there may be a breaking change. So that was one technique. We also came up with another approach, a kind of model-based testing technique. Instead of running all the tests again on the new version of the library, now we introduce a test generator, which automatically produces a large number of tests based on the model for the old version of the library. And then we check that the new version of the library passes all those tests. I don't have time to explain how the test generator works, but it has two nice properties. It is much faster, and it detects more breaking changes than the other technique. Here are some experimental results. We tried to run our tool on almost 2,000 minor and patch updates of 25 different libraries, and it reported 84 breaking changes. Note that this was for minor and patch updates. There shouldn't be any breaking changes here. If we had used the type regression technique I described, we only found 25. And if we only use the existing test suites, then most of them would be undetected. And on top of this, running the test generator was typically 25 times faster than the type regression testing technique. So this seems to be a quite effective technique for detecting unexpected breaking changes in libraries. Here's an example. In this update of the library named big integer, the function parseValue was changed. The developer believed that this was backwards compatible, so it was released as a patch update. By scanning through the NPM registry, our tool found another package named deposit IBAN that uses the big integer library and has a test suite. The tests were unaffected by the change, but by running the test suite and performing the dynamic analysis, our tool produced a model of big integer. And from that model, it automatically produced a new test that reveals that this is in fact a breaking change. If you load the library and perform just a few operations, then this type of tests gives a different outcome after the change of the library. So that's clearly a breaking change. So now we basically know how to detect breaking changes. Let's say there is a new major version of a package B. It's a major version update, so it probably contains breaking changes. This means that the developer of package A needs to adapt his code somehow. As a start, it would be really nice if the developer could simply push a button to find out which parts of his code may be affected by the breaking changes. Here is how we address that challenge. The idea is that the developer of the library or someone else who is familiar with the library writes a collection of breaking change detection patterns using a small pattern language we've developed. This collection of patterns will accompany the customary changelog file that is provided with the library update. The patterns describe in a machine-readable manner which parts of the library API have changed. Now the developer of package A can run a tool we've built which takes the package source code and the detection patterns as input, and then outputs a list of the locations in the code that match the patterns. These are the places that may need to be updated. In our experience, the most time-consuming part of updating a program to become compatible with the new version of the library is not actually making the changes, but finding out which parts need to be changed, and importantly, which parts do not need to be changed. I won't describe in detail what these patterns look like, but here's an example. This changelog for this update of the node-fetch library contains 9 breaking changes. And for each of them, we write a small pattern. For example, this entry in the changelog says that all functionality in a certain module is now unsupported. That is captured by this pattern we write. And this entry says that certain internal methods are no longer supported, which we can express using this pattern. The analysis that then performs the pattern matching is a lightweight static analysis that runs in 3 phases. It first performs a flow-insensitive field-based alias analysis of the program code. Next, it performs what we call an access path analysis that tries to approximate which parts of the library code are being used where in the client code. These access paths are actually very similar to the so-called dynamic access paths I mentioned before, but here they are produced by a static analysis instead of a dynamic analysis. And in the third step, the tool compares the access paths with the patterns that describe the breaking changes and reports all the locations it finds. One of our key insights is that it is possible to design such a lightweight analysis with quite good precision and performance, because it doesn't need to track all the data flow in the program, but only how the library is being loaded and used in the client code. If you're interested in learning more about how to design such a static analysis, you can read our paper. We've done some experiments and they are quite encouraging. We took 15 widely used libraries and considered one major update for each of them. By carefully reading through the change logs, we find 176 breaking changes. And while studying those, we found a few more, so we ended with 187 breaking changes for these libraries. Almost all of those could be captured as patterns in our pattern language. Some of them required more than one pattern, so we have 283 patterns. And all these patterns are generally quite short and simple. Then we found some clients that depended on the old version of those libraries, and we ran our tool. As a result, it found more than 900 true positives. That means locations that were actually using the library functions with breaking changes. There were quite few false positives, and importantly, 0 false negatives. That means the analysis most likely didn't miss any locations. And the analysis time was low, typically around 1 second per client. With that, we move on to the third challenge. Now we know how to find breaking changes, and we know how to find the locations in the client code that are affected by breaking changes. We now also want to automatically patch the affected code such that it becomes compatible with the new version of the library. To achieve this, we have extended our pattern language such that we can also describe a program transformation, a patch rule, along with each breaking change detection pattern. And then we added a transformation component on top of the static analysis, so that the tool now not only detects which parts of the program need to be patched, but also actually transforms the code. This is not 100% automatic. It requires a little guidance by the developer on the way. The reason is that the static analysis is not perfect. It is designed to over-approximate so that it may find too many matches, but not too few. And it also keeps track of its own certainty. So when it is in doubt, it asks the user for help. Of course, it is important that we change only the right locations and all of those that need to be changed. I'll show an example in a moment. Here's an example of a description of a particular breaking change in the RxJS library. This is the line in the changelog file that describes the change. This is the pattern that describes which functions are affected by the change. In this case, it involves calls to various methods, including map, filter, and take, that are accessed from the RxJS library, but excluding methods from the operators module. This is the patch rule that specifies the code transformation that should be applied. In this case, the calls should be replaced by calls to the pipe method. And because the analysis may not be able to determine exactly whether a call is to one of these methods, it may be necessary to ask the user for help in some cases. And this is the question for the user in those cases. Here is an example of a transformation that our tool has made in a specific client of RxJS to adapt the client code to the breaking change. Here is a call to the take method, and it gets transformed into this call to the pipe method. A very reasonable concern is that these detection patterns and patch rules may look somewhat cryptic. But keep in mind that they only have to be written once, and then they can be reused for all the many clients of the library. Also, we were able to write such patterns and patch rules for a number of libraries without having expert knowledge of the libraries. So we believe that with a little training, it should be even easier for the library developers to do this. Now I want to give a quick demo of our prototype implementation. The tool is named JSFix. Here is what it currently looks like from the package developer's point of view. Imagine we're the developers of a package Redux Logic. This is a library that is built on top of a number of other libraries, and one of those libraries has been updated to a new major version. We can see here that our tool has detected that two of the libraries that Redux Logic depends on are known by JSFix, meaning that someone has written patterns and patch rules for them. Here we are interested in upgrading to the new major version of RxJS. Then we select which source files we want to fix. In this case, it's all the files in the source directory. And then we run the analysis. It only takes a second. Before it performs any transformations, it has some questions that the analysis is too imprecise to answer itself, so it asks the user for help. Of course, it is important that it makes correct transformations. So with this interactive mechanism, whenever the analysis is unable to provide sufficiently precise information, it asks the user. At this point, it asks whether the receiver type, in this case, is an RxJS observable object. For the library developer who knows the program code, this kind of question is usually easy to answer. Let's say the answer is yes in this case. Now we can see what changes have been made to this file. A new import has been made in the top. And here type.map has been changed to type.pipe. Maybe you want to make some manual edits also. Now let's confirm this file. And we proceed with the next file. Here we see the same question as before. Several places. Let's just say the answer is yes at each place. And we review and confirm the changes. And so on. Throughout all the files. And now JSFix is ready to produce a pull request with the changes. To evaluate how well our approach works, we took 12 major updates of some widely used libraries, and we looked at their change logs. The libraries had quite a lot of breaking changes. So from that, we wrote 326 detection patterns. For most of them, we could also write patch rules, but for the remaining 28, we couldn't. In most cases, not because our patch language is not expressive enough, but simply because no patch was possible. For example, because some functionality had simply been removed from the library. Then we took some clients of those libraries, 89 clients that have test suites that succeeded with the old version of the library, but failed with the new version. So those clients were clearly affected by the breaking changes. For most of those clients, all the patches were expressible. In total, our tool made 451 transformations of the client code. And for each client, just a few questions were asked to the user with this interactive mechanism. And the best part is that after these transformations were applied, all the test suites succeeded again. This gives some confidence that the transformations are correct. On top of this, we created pull requests for many of the clients based on the output of our tool. And 31 of these pull requests, many involving substantial changes to the client code, have been accepted by the client developers. So we believe this is quite encouraging for a first prototype for this tool. I've reached the end. So to conclude, I believe it is possible to help programmers and improve code quality by the use of automated program analysis, testing, and transformation techniques. In particular, for detecting whether a JavaScript library update contains breaking changes, finding the locations in the application code that may be affected, and patching the application code to become compatible with the new version of the library. The results we have so far are only the first steps. We are currently performing more experiments and planning user studies to learn more about various opportunities for improvements. If you want to know more, especially about the program analysis techniques we use, here are some research papers you can look at. Thank you for your attention.
Anders, that was awesome, to be honest. I know a few groups which are trying to do something very similar to what you just presented to us. So I will definitely share this presentation with them. But I have a few technical questions for you. The first one, because I'm actually writing JavaScript code quite often. You said that there are some false positives, like 14%, if I'm not mistaken. Can you elaborate a little bit, like what are they related to, or why they happen?
So the pattern matching is based on this static analysis that tries to approximate the data flow in the program and find out which parts of the library are being used where in the client code. And if you want to use this as a starting point for updating the client code when you have breaking changes in the library, then it's very important that you fix the right places, of course. You want to find all the places in the client code that use the parts of the library that have changed. You don't want to review the entire program. You don't want to go through line by line in a large program and see what is being used here. So it's important that the analysis is accurate. It's okay that it over approximates a little bit, as long as it's able to, for example, using this user interaction mechanism, get confirmation from the user. So that's why the analysis is designed such that whenever it is in doubt, it will ask the user for help. Is this actually an object of this particular type? Like in the little demo, it asked the user a number of times. And the user who's familiar with the code can usually answer these questions quite quickly and then get rid of these false positives. On the other hand, it's very important that you don't have false negatives, because that would amount to places in the code that should be patched but are not being patched because you miss them. So for that reason, this analysis is carefully designed such that it over approximates but not under approximates. It's okay that it finds too many matches, but it should, as far as possible, not find too few. Of course, it should not have too many false positives, because then the user has to get involved too much and answer too many questions. And it's also important that the analysis is designed such that it actually knows where is it fairly certain about whether there is a match or not, and where is it actually in doubt. That's also a quite unusual property of an analysis, to actually make that distinction and keep track of its own certainty.
And that sounds reasonable. And what happens if you, in your example, if you return one type and then I change the code and return a different type, but it's still a valid change because of the polymorphism, for example. So I'm returning the child type or something like this. Even though in JavaScript we don't have types and we don't have like proper like classes like in Java, but we may have some sort of interchangeable type. So instead of this type, I can return another one. So in this case, I think it's going to be it's going to trigger an error, right? In your case.
Not quite. That depends on how we do the comparison. And the checker here, it knows about subtyping. If it can see that, as in your example, some type is changed to a subtype, that's a perfectly valid change. So that's one way to not detect and report all changes, but only those that are actually incompatible. So it's like when you do a type checking in a Java program. If you're in a Java program is using some library, then some changes of the library are perfectly acceptable. Java has these binary compatibility conditions that tell you when is it okay to replace a library without needing to recompile the client code. So it's basically the subtyping that is taken into account here. Of course, this is JavaScript. This is a very dynamic language, and it's really difficult both to track everything very precisely and to keep track of subtyping relations. So all this is inevitably a best effort attempt. What we can do is basically try to do this as well as possible, but there's always the risk that some programmer can fool our analysis. That's just unavoidable when it comes to JavaScript. And this is why we do these empirical experimental evaluations to see how well does it actually perform in practice. How many false positives do we get? And do we have false negatives? So for example, to find out whether we end up breaking something, we do this experiment I mentioned briefly, where we take a number of clients that we can see are actually affected by the breaking changes, because their test suites fail if you just naively change to the new version of the library. So we know that there is a breaking change in the library that affects this particular client. Then if we run our tool, push the button and apply the patches that it produces, if it now passes the tests, that's a pretty good indication that the update is correct. Of course, it's not a guarantee because no test suite is complete. But if we can do this for 100 clients and all of them succeed this test, then it's not a guarantee, but it's a pretty good indication that it's not completely far off. In the end, the developer certainly wants to review things manually before actually approving the pull requests that are being generated, for example. But you should keep in mind that the alternative is that you have to do all that manually. And we see actually quite often that you have a client of some library, and the library has in a major update some breaking changes. And maybe 6 months after you wrote that client code, you're actually not sure exactly which parts of the library you are using. So how do you even know that you are using the parts of the library that are affected by the breaking changes? Quite often, the answer is that your code is completely unaffected by the breaking changes. So that means you don't have to change anything. But just to reach that conclusion, you have to review every single line of your code manually and see, am I using the part of the library with the breaking change here? Do that line by line. That's really time consuming, tedious and error prone. So that's why with some tool support, we can reduce that effort a lot. That's at least the intention, the goal of this work.
And this JSFix tool, is it open source?
Not yet. We're working on it. So as mentioned at the end of the talk here, we're doing some more experiments and getting started with some user studies. We want to try this on some some of the larger libraries that are being updated with new major versions, and then get in contact with some library developers and also some users of those libraries. So we plan to do that, and then some point in the near future we'll make a public available version of this tool.
That's great. We're looking forward to it. A few questions from our listeners. The first one is, do you see anyhow the possibility to use this technique for fixing security issues in the code?
Yes, in the sense that, well, often there is a vulnerability in a library, and that requires you to make some changes in the client code that uses the library. So you could actually use a similar mechanism here if you know exactly which parts of the library are affected by some vulnerability and what a good transformation could fix that in the client code. Then you could use exactly the same machinery to first find the places in the client code that is using these affected pieces of the library, and then also make the changes to work around the problem. So here, the most important part is actually just to find the places in your code that is affected by the vulnerabilities in the library code. In that case, you probably, of course, ideally, you would want to also automatically patch the client code or rewrite the client code. But just being notified that here's a piece of code that you need to update to avoid vulnerability, that would be really useful, I think.
Thanks. Another question, do you currently use SAT or SMT solvers? And if not, can you use them to enhance your approach?
Currently, we don't do that. Actually, the static analysis part we use is, as mentioned in the talk, a fairly lightweight analysis. So I've also worked a lot on more heavyweight analysis techniques that keep very precise track of the data flow and control flow in JavaScript programs. And doing static analysis on real-world JavaScript code, if you want to be fully sound and also precise and scalable, that's extremely hard. That's why in this work, we instead resort to much more lightweight techniques. So we don't use any SAT or SMT solving here. And the reason why it still works is that it's enough to track the core data flow around the use of library values, how you load libraries, how you affect methods of the library, and so on. Yes, at some point, it may be useful to improve precision using SMT, SAT solving, but we haven't seen a need for that at all yet.
And now the practical question from me personally. So it seems that in the future, it will be possible if your tool becomes more popular, then I am as a developer of a library will ship the new version of the library, and I will accompany this new release with a set of rules using your language. And then the client will just take my upgrade and will take this set of rules and using some tool, maybe your tool or maybe some tools which will be created on top of your language, just automatically apply everything and will upgrade my client in just one go. And then we'll leave some places for me which are questionable, and I will just go through and just click a few buttons, make a few changes, and boom, my library, my client is upgraded like 100,000 lines of code automatically goes up to the next version of the library. Is it right? This is your vision?
Exactly. That's the plan. That's the vision.
So are you planning to make this language open, or you think that your tool will be the only tool to operate on this language?
Everything, the language is fully open. It's described in quite a lot of detail in our research papers. So we have this paper coming up at ICSI a couple of months from now that describes this JSFix tool, including the languages for describing patterns and expressing the transformations. So everything is described in the papers. So you could, in principle, re-implement the tools based on those descriptions.
Awesome. I mean, I like it. We will definitely keep on track. I mean, we will keep watching for your progress, and we will try to use your stuff. And maybe like I said, maybe think about creating a similar tool using your approach, using your language, since it's open.
Yeah. Also, we are very happy to collaborate with other researchers and JavaScript developers on trying to push on this kind of work to actually make it more practical and start using it for real.
Okay. Thanks a lot. Time is over. Thank you very much again for attending the conference. It was a really great keynote talk. I will definitely share the recording with a few of, colleagues of mine working on something similar. Thank you, and hope to see you sometime submitting a paper to our conference, maybe next year.
Of course.
Thanks a lot. Bye-bye.